So let's finish up our review of the most important material from discrete structures that you're going to need for foundations of computer science. Standard disclaimer, I'm going to ask you one more time, please, please, please go do the exercises in the textbook if you haven't done them already. Make sure you're really comfortable with this material. So we'll start with graphs. And this is a very informal definition of a graph. Your book has a much more formal definition, but you should think of a picture something like this when you think of a graph. A graph consists of a set of vertices, so we sometimes call those nodes, that are connected by edges. Any pair of vertices connected by an edge are said to be adjacent. So for example, here, 1 is adjacent to 2, 3 is adjacent to 4, 6 is also adjacent to 4. But the vertices 4 and 2 are not adjacent. We call a graph n-colorable if there is some assignment of colors to the vertices so that any two adjacent vertices have distinct colors. So for example, this graph here is 3-colorable. Let me show you. If I say, well, let's let 1 be blue, then the vertices that are adjacent to it need to be different colors. So maybe 2 is yellow and 5 is red. Let's look at the next few vertices adjacent to these ones. 3, well, look at that. 3 is only adjacent to one thing that's colored right now. That's 2, so we can make 3 blue as well. 4 is adjacent already to a blue and a red, so we'll make that yellow again. And maybe we'll color 6 red again. So this graph is 3-colorable. I don't think I can color it in any fewer because I have shown you an assignment of n colors, 3 colors, to its vertices. Of course, it's also 27-colorable if you want. Another definition, a graph is planar if it can be drawn on a plane so that no edges intersect. So this graph here is planar. Here's another picture of a graph. There's the definition again. So do you think this graph is planar? And this is really a trick question at some level. Obviously, it doesn't look like it's planar because it does have two edges intersecting. But this is an example of where when you're doing a course in any sort of theory, be it math, theoretical computer science, or whatever, whenever you are trying to figure out whether something meets a certain standard, you need to look at the definition. And the definition here says a graph is planar if it can be drawn on a plane so that no edges intersect. And sure enough, here's another version of this very same graph that I've drawn where none of the edges intersect. So if you look, the edges are the same. There's an edge between AD and AC, and here I've got an AD and AC. B is adjacent to C and D, B is adjacent to C and D, C is adjacent to A and B, C is adjacent to A and B, and of course D is adjacent to A and B, D is adjacent to A and B. So these are the same graph. So this graph can be drawn on a plane so that no edges intersect, and therefore we say that this graph, no matter how we draw it, is considered planar. I'm sure you're familiar with directed graphs. A directed graph is a graph where each edge points in one direction. Very formally, this is not a directed graph because we have a double-headed arrow here. Okay, do you see that double-headed arrow? Now, strictly speaking, a lot of people will, just as a shorthand, use this double-headed arrow to represent what I've drawn here, which is an up arrow and a down arrow, right? So 2 arrows. So as long as you're willing to agree that a double-headed arrow really represents 2 individual arrows, then I will say, okay, we can count both of these as directed graphs. But strictly speaking, this is a directed graph and this is not because this particular edge happens to point in both directions. As long as you understand that, I'll let you draw your directed graphs like this. We talk about the degree of a vertex, which is just the number of edges that it touches. And if a vertex has a loop, we will add 2 to the degree. So if there's a vertex that goes, say, from node A to node A, then we'll say it has a degree of 2. When we talk about vertices on directed graphs, then we talk about their in degree and out degree, right? How many edges point to the vertex, how many edges point away from that vertex. So if we just look at this graph for a minute, the vertex 1, this is an undirected graph, right? So we just talk about the degree of the vertex. This one has a degree of 2. The vertex 5 seems to have a degree of 1, 2, 3, right? Because there's 3 adjacent nodes. And if 5 had a loop on it, then we would say this had a degree of 5. So let's talk about how we can formally represent a graph as data. What we really want to do is to have a more formal way to represent our graphs so that, for example, we could write programs about them, or more importantly for this course, we could write proofs about them. And so what we're going to do is we're going to use the representation that's in the book. And this may be new to you, but it should take you not very long to understand what's going on, right? So maybe a new idea to represent a graph as data, but once I tell you the definition of how we're going to represent that graph, you should be comfortable with this. So what we're going to do is we are going to say that vertices are a set and edges are a set of sets. So for example, vertices, what are the vertices in this graph pictured here? Well, they are 1, 2, 3, 4, 5, 6. So the vertices are the set containing the elements 1, 2, 3, 4, 5, and 6. And what are the edges in this graph? Well, an edge, since this is an undirected graph, we could say that there's an edge from 1 to 2 or from 2 to 1. So we'll just represent this edge 1, 2 as the set containing the elements 1 and 2. And so you can see here is a set containing a bunch of sets. And each of those sets that contained in here has exactly 2 elements, and that's because it's representing an edge on the graph. Now, one of the things we're going to do a lot is we're going to say, you know what, a graph, rather than say a graph has vertices and edges and talking about them separately, we're going to say, you know what, we're going to represent a graph as a 2-tuple, an ordered pair, where the first element is the set of vertices, and the second element in our graph is the set of edges. And so all I'm doing here is I'm saying, well, I have a pair. Oops, let's go back up. I have a pair, and the first element in my pair is that set of vertices that we have here. So I just copied this down to there. And then there's a comma, and the second element in my pair, you can see there's just one more thing in my pair, which is a set containing a bunch of stuff, and that's just the set of edges. So here's another example. How do we represent a directed graph as data? Well, with a directed graph, each edge actually has a source and a destination, right? Each graph goes from one vertex to another. So now we'll leave our vertices as a set, just like before, but the edges are going to be a set of pairs because the order matters. So, for example, in this graph pictured here, the vertices are the elements 1 through 5. And the edges, well, this says there is an edge starting at 1 going to 2. Well, there it is. Another edge starting at 1 going to 4. 1 to 4. And we have to represent this as a pair, as a 2-tuple, and not as a set because order matters. In sets, order doesn't matter, but here in our 2-tuples and our pairs, order matters, so this is really important. And again, we can represent a directed graph as an ordered pair where we say first we'll give you the vertices, then we'll give you the edges. So here's my ordered pair. There's the vertices, the elements 1 through 5. And over here, we've got all the edges. There's an edge starting at 1 and going to 2, starting at 1, going to 4, and so on. And notice that this is a set of edges. Each element, each edge in our directed graph is in fact a pair. We can also talk about weighted graphs, which have some information attached to each edge. Um, and you can think of that as perhaps the distance to get between two cities, if the vertices represent cities, or the cost to travel between them, all sorts of things. Um, but so now each edge we're going to represent as a three tuple. So it's going to have a source, a destination, and a weight. Um, and we can also represent a undirected graph that is a weighted graph, just as a directed graph, right? Because all we do is we take every undirected edge that we have and turn it into two directed edges. Um, so for example, if we look at this graph up here, which is a directed graph, um, the vertices in that graph are A, B, C, D, and H, right? And if I look, what are my edges? Well, there's an edge from A to D that has a weight of 60. So I have A, comma, D, comma, 60. And again, order matters. Start, end, and the weight. This says I have another edge from A to C that has a weight of 12. Well, I go from A to C with a weight of 12. So that looks good, and so on. And again, we can represent a weighted graph as a two-tuple, as a pair, where we have the vertices and the edges. Both of these are sets. Our vertices are just a set of elements, and our edges are going to be a set of three tuples. And there's all my three tuples. What you have to do now, very important, is just go back and look over the last few slides and make sure you understand, when do I use a tuple? When does order matter? When do I use a set? When does order not matter, right? When do we use parentheses? When there's a tuple, right? When do we use curly braces? When there's a set. And I'm just going to give you a heads up here because this is so important. It's so important to our proofs that you get these things absolutely right. I am going to be a completely crazy nitpicker on this. You really, really need to understand this. So make sure you go back and watch the first part of this video again and make sure you really understand when I'm using parentheses, when I'm using curly braces, and why. There's also a concept of a subgraph. So here's the definition, a graph. And here's a graph. Remember, now our graphs are just a pair. In this case, I'm calling the pair V prime E prime. I could have called it something else, but we need to talk about two different graphs here, the subgraph and the graph. So we'll call the subgraph V prime E prime. So a graph V prime E prime is a subgraph of another graph VE if all of the vertices in V prime are a subset of the vertices in V, and the set of edges E prime is a subset of the set of edges E. So here is a sample graph, and here's 4 graphs that are subgraphs of that first graph. Okay, so I want to go back to making sure that you understand exactly how we represent graphs and how we're going to represent graphs for this class. So here's a bunch of pairs, sets, all sort of mishmash. And I want you to look at this, just pause the video, go through it and say, which of these are graphs? Which of these are directed graphs? Some may be both, and some are neither. So if you look at this list, the first thing that you should remember is that a graph is always, we defined it, a graph is a pair where the first element of the pair is a set and the second element of the pair is a set. So anything in here that's not a pair, we should get rid of immediately. So anything that has set braces on the very outside, that's not going to be a pair, right? That's a set. That's not a tuple. So here's all the ones that I can find that have set symbols on the outside. So all of those are definitely not graphs, right? It's not a graph, it's not a directed graph, nothing. So we'll cross them out, okay? Next, remember that a graph is always a pair of two sets. So if you look at this closely, you can see that all of these items that I've highlighted are not pairs of two sets. So this first one is indeed a pair. The first element in the pair is a set, but the second element is a tuple. So that's not a pair of two sets. This item here looks like it's actually a tuple containing three items, right? So that's not good. Here we have a pair again, right? It's a two tuple because if you look at the parentheses, this is another two tuple with two tuples in it, but that's not what a graph is. And finally over here, again, I have a tuple, but it contains a set. Good. That would be all right for the edges. I mean, for the vertices. But over here, we've got a tuple with two sets in it, and that's not what a graph should be. So goodbye to all those guys. So now let's just look through each of the remaining ones and say, is it a graph? Is it a directed graph? Is it both, or is it neither? So if we look at this first one, we have a two tuple, right? Because there's two things inside of this tuple. The first thing's a set, the second thing's a set, so that's good. This could be the vertices, right? That looks good to me. And this is a set, and it contains a set of, it contains a set that just has two elements in it. So that's not a graph, right? We need a set that contains, we need a set of edges, and that's not a set of edges, so that's not one. Let's look at this one. Here we have a tuple. It has two things in it. Good. First one looks like it could be vertices. This second one, now this is looking more promising. This has a set of sets, so it might be a graph, right? And AB, well, that's edges. That could be an edge from A to B. So this is going to be a graph. That looks good. Here again, we have a tuple. It has two things in it. Both of them are sets. ABC is a set of vertices, and we've got we have tuples in here, but that's okay. That's just directed graphs. So there's an edge from A to A, another edge from A to C. That looks good. So that's just going to be a directed graph. Again, we got a tuple here. Inside it, we have a set of vertices and another set that could be edges from A to B and A to A. These are sets, so I guess that's a graph. Here's a tuple. We've got, let's see, vertices and edges where the edges are tuples, so that's fine. That's just pairs, so that looks good. That's a directed graph. This is interesting. We have a pair. Is it a pair of two sets? You bet, because the empty set is a set and there's a set of vertices. Is it okay to have the empty set here? Absolutely. This is just a graph that has no edges, so that's good. And of course, because this is the empty set, we don't know, is it a directed graph that has no edges, a graph that has no edges? So I just wrote graph or directed graph there. Similarly, this is just going to be a graph or a directed graph that has no vertices or edges. It's pretty boring, but it's okay. We can have that. So tell me what's wrong with these. Why are these ones not graphs or directed graphs? Let's just take a look at them. Well, actually, if you look at all of them, the biggest problem is that our vertices are just A and B, but all of them mention C inside of the braces somewhere here where we're trying to list the edges, and there is no vertex C, so that knocks them all out of contention anyway. But let's just look at this for a minute. This is This has two sets, and each set has a tuple in it, so that's an okay directed graph apart from that C, right? But the C gets rid of it instantly, right? If you look at the braces on this, not only do we have the C in there, but the braces are messed up. Similarly, we've got a set with a set inside. You can look at all of these and there's problems with them. The first problem that instantly rules all of them out of being a graph or a directed graph is that they have this edge AC, which is impossible. You can't because the vertices are only AB. But beyond that, there's other things wrong with this too. Okay, so let's move on to section 1.4.2 where we talk about paths. Informally, a path in a graph is just a sequence of vertices you travel through. So for example, I could start at 4 and go to 5 and then 2 and then 3 and then 4 and then 6, and that would be a path. Here's my sequence, right? My sequence of edges. We're going to use a tuple for this because order matters. And the formal definition is simply that we have a sequence of edges that we denote using a sequence of vertices, x0, x1, and so on all the way up to xn, so that we know that for every pair from one x sub I minus 1 to the next one x sub I, there's an edge in there. And if you look at this 1 less than or equal to I less than or equal to n, you'll see that this gives us all the edges. And I answered my question already, but I said I used a tuple here. Could I have used a set? And the answer, of course, is no, because if I used a set, then order wouldn't matter, and order very much matters in a path. So a cycle is just a special kind of path where the beginning and ending vertices are the same, and in which no edge occurs more than once. So if you have a graph that doesn't have any cycles, we call it acyclic. And if you have a path that has n edges, of course that path is going to have n plus 1 vertices, right? Notice we started at x sub 0 here because there's a start and an end. But we talk about the length of the path as being the number of edges that it has. And of course you can have paths and cycles on directed and undirected graphs.